Pluto is a faraway, elusive, and less conspicuous planet that was once considered part of our solar system. However, recent groundbreaking statements from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into public discussion. They have proposed that this icy planet might be heading toward a potential collision course with Neptune. But how can such a scenario be possible, and what would the consequences be of such a monumental event? Are we witnessing an unusual, unpredictable phenomenon, or is there something more to this impending cosmic disaster? Join us as we explore the possible outcomes of a Pluto-Neptune collision. Pluto, which was once classified as a planet but later redefined as a dwarf planet, continues to be a subject of fascination and study within the vast universe. Recent speculations from leading experts have suggested that Pluto's orbit is alarmingly close to Neptune's, prompting astrophysicists Neil deGrasse Tyson and Michio Kaku to warn of the possibility of a catastrophic encounter between these two celestial bodies, which could pose a significant risk to Earth. But how could such a collision even occur? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete one full orbit, and since its discovery in 1930, Pluto hasn't even finished a single full revolution. However, the intrigue doesn't end there. Pluto's orbit is characterized by its distinctly elliptical shape, straying far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its tilt. Its orbit is inclined at an angle of 17 degrees to the plane of the solar system, giving Pluto's path a far more erratic trajectory compared to the more orderly orbits of the other planets, adding complexity to its orbital dynamics. Perhaps one of the most fascinating aspects of Pluto's orbit is the way it intersects with Neptune's. For roughly 20 years during each orbit, Pluto actually travels closer to the Sun than Neptune does, defying the conventional expectation of their relative positions in the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational forces exerted by other planets. After Pluto's discovery, astronomers quickly set out to understand its strange orbital behavior. Unlike the other planets, whose orbits are relatively close to the solar plane, Pluto's orbit stands out because of its steep inclination and highly irregular shape. The puzzle deepened when it became clear that Pluto's orbit intersects Neptune's, yet it remains stable. This demonstrates the intricate dynamics of celestial mechanics, or the so-called three-body problem in space. Understanding how three objects like Pluto, Neptune, and the Sun interact gravitationally is key to this scenario. It's like trying to predict where these objects will be based on where they started and how they influence one another. The stability of all planetary orbits is ensured by the concept of non-concurrent libration. In the case of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, the two bodies are always positioned at least 90 degrees apart. This spatial separation prevents a collision between them. Another contributing factor is orbital precession, which refers to the slow vertical movement of a planet's orbit. For Pluto, this means that when it comes closest to Neptune or any giant planet, it is positioned well above their orbital plane, providing another layer of defense against potential collisions. An additional factor at play is the VSK wobbling, a concept named after three researchers, Zell and Kai, who studied how celestial bodies interact with one another's gravitational pull. This wobbling effect explains why Pluto's orbit, though seemingly chaotic, remains stable over long periods. The gravitational tugging between Pluto, Neptune, and the Sun influences Pluto's orbit, ensuring it remains relatively smooth despite its irregular shape. The VSK wobbling shows that even in the most unpredictable environments, there are underlying patterns and forces that maintain stability. This three-body problem is crucial to understanding the nature of Pluto's orbit, its relationship with Neptune, and the behavior of distant objects in our solar system. Numerical simulations conducted in the late 1980s revealed that Pluto's orbit, despite the stabilizing forces at play, is actually quite erratic. Small deviations in its initial conditions could lead to significant differences in its path over centuries. Nevertheless, these simulations also showed that Pluto's orbit maintains stability over incredibly long timescales, such as millions or even billions of years. To fully grasp the dynamics between Pluto and Neptune, It is important to consider the gravitational influence of the giant outer planets like Neptune, Jupiter, and Saturn. Neptune's influence is significant, as it governs Pluto's orbit in a special resonance. For every 2 orbits that Pluto completes around the Sun, Neptune completes 3. This gravitational resonance helps to keep Pluto's orbit stable, but Neptune is not the only player in this complex equation. Jupiter's massive gravity also plays a key role in stabilizing Pluto's path, while Saturn further contributes to this dynamic. These forces working together ensure that Pluto remains on a steady course for potentially millions of years, keeping it out of harm's way from Neptune's influence. Without these stabilizing forces, the solar system would be much more chaotic, with planets potentially colliding or being ejected from their orbits, triggering catastrophic consequences across the solar system. The possibility of Pluto colliding with Neptune in the future highlights the complexity of celestial mechanics and the importance of studying the stability of orbits. By understanding these intricate dynamics, we gain a better understanding of how the solar system works, the role of gravitational forces, and the behavior of distant objects. Even though Pluto's orbit may appear chaotic at first glance, it is a testament to the delicate balance of forces that keep it in place. Exploring space often leads to surprising discoveries, and Pluto's irregular orbit serves as a prime example of the mysteries of the cosmos. The concept of orbital chaos illustrates how a celestial body's orbit can be highly sensitive to its starting position. In Pluto's case, even small changes in its position or speed could drastically alter its long-term orbit. Automated simulations have proven invaluable in helping scientists study these behaviors. By modeling how Pluto and other objects like Neptune influence each other through their gravitational pull, these simulations show how even the tiniest adjustments in the conditions can have a significant impact on Pluto's trajectory. Though Pluto's orbit is stabilized by mechanisms like libration and precession, simulations have also revealed that Pluto's orbit is far from consistent. Small deviations in its initial conditions can lead to vastly different outcomes, making long-term predictions about its movement extremely challenging. Despite this apparent chaos, Pluto's orbit remains relatively stable over geological timescales, like billions of years, suggesting that even in the midst of seeming chaos, there is an underlying order to Pluto's motion around the Sun. Predicting celestial movements, especially for objects with irregular orbits like Pluto, is a massive challenge. The inherent unpredictability of these systems means that any long-term forecast is filled with uncertainty. Numerical models help us understand and predict these movements, but their accuracy depends heavily on precise initial conditions. Even a slight error can result in vastly different outcomes, making it difficult to predict Pluto's future trajectory with confidence. Aside from the chaotic nature of planetary orbits, Pluto's story serves as a reminder of the dynamic and ever-changing nature of the universe. Despite the many advances in our understanding of space, Pluto's case demonstrates how much we still have to learn. Grasping the gravitational influences of the giant planets on Pluto's orbit gives us important insights into the broader mechanics of the solar system, showing how the position of each planet can significantly affect the course and stability of others. So why are prominent astrophysicists raising concerns about a possible collision between Pluto and Neptune, despite all these stabilizing forces at play? Neil deGrasse Tyson, a leading astrophysicist and one of the figures responsible for Pluto's reclassification from a planet to a dwarf planet, offers an insightful perspective on the ongoing mysteries of our solar system, including Pluto's future. Tyson has played an important role in reshaping the public's perception of Pluto and in understanding its place within the evolving landscape of our solar system. Tyson views Pluto's reclassification not as a loss but as an essential adjustment based on our expanding knowledge of space and celestial bodies. Tyson's approach to celestial mechanics is one of constant discovery and evolution. He sees the complexities of orbits like Pluto's as indicative of how much more there is to learn about the universe. Although Tyson remains optimistic about the study of space, his views on Pluto's potential collision with Neptune suggest that there are still many unanswered questions. Will Pluto collide with Neptune, or is this merely a momentary confusion in the ever-evolving cosmic system? Only time and further research will provide the answers. For now, we are left with an even greater curiosity about how much remains unknown in our own solar system. The potential for a Pluto-Neptune collision invites further examination of the mysteries of the universe and challenges our understanding of planetary dynamics. The prospect of two celestial bodies with vastly different properties colliding raises intriguing questions about how gravitational interactions shape the evolution of the solar system. A collision between Pluto and Neptune would not only have major implications for our understanding of planetary behavior, but would also provide valuable insights into the evolution of the solar system itself. To understand the dynamics of a potential impact between Pluto and Neptune, it's essential to consider the characteristics of both planets. Pluto, though classified as a dwarf planet, contains a variety of elements and compounds in a frozen state thanks to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere is primarily made up of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas giant, consists mainly of hydrogen, helium, and other lighter elements with a deep, dense atmosphere. A collision between these two vastly different bodies would undoubtedly have profound effects on both planets, potentially creating an event that could be seen from vast cosmic distances. However, it's important to note that Neptune's gravity is not the only stabilizing force at play. Jupiter, the largest planet in the solar system, also exerts a significant gravitational pull, contributing to Pluto's stable orbit and preventing it from venturing too close to Neptune's domain. Saturn's gravitational influence further complicates the interactions in the outer solar system, making it unlikely that a devastating collision between Pluto and Neptune will occur. While Neptune's gravitational influence plays a dominant role in stabilizing Pluto's orbit, the complex relationships between other planets, such as Jupiter and Saturn, further ensure that Pluto's path remains steady. However, research has also shown that the relationship between Pluto and Neptune is not as straightforward as a potential collision course. The gravitational resonance between the two planets, where Pluto completes 2 orbits for every 3 Neptune completes, creates a natural barrier that prevents them from colliding. This resonance, often described as a gravitational dance, ensures that Pluto and Neptune's orbits, while intersecting, never result in a collision. This mechanism is a remarkable example of how celestial bodies can maintain a harmonious relationship despite the chaotic forces at work in space. Yet, the future of this delicate balance is not guaranteed. Small shifts in the positions or velocities of these planets could disrupt this resonance and lead to unpredictable consequences. These shifts could be triggered by external forces, like the gravitational influence of an undiscovered planet or a passing star, or by internal events such as tidal forces causing gradual changes in the orbits of these bodies. Continued study and observation of Pluto, Neptune, and the surrounding bodies in the outer solar system are essential for understanding the long-term stability of their interactions. As technology advances, scientists will be able to refine their models and gain a clearer understanding of the dynamics between these distant objects. New data may shed light on the delicate balance that keeps Pluto and Neptune from colliding, or it may uncover entirely new forces that could alter their relationship in the future. As we continue to study the dynamics of Pluto and Neptune, one key factor that has emerged is the possibility of an undiscovered object influencing their orbits. This hypothetical object, often referred to as Planet 9, is believed to exist in the far reaches of the solar system. Some scientists have speculated that its gravitational pull could alter the orbits of objects like Pluto, potentially pushing them toward new paths that might destabilize their current positions. While the existence of Planet 9 is still a subject of debate, its potential impact adds another layer of complexity to the situation. In addition to the gravitational interactions between planets, it's important to consider the broader context of how the solar system itself is evolving. The Sun, being the dominant gravitational force in the system, is gradually losing mass through the process of solar wind. As the Sun loses mass, the orbits of all the planets, including Pluto and Neptune, could slowly expand over time. This process could shift their relative positions and affect the long-term stability of their orbital resonance. Furthermore, the outer solar system is not a static place. Objects like comets and other small bodies are constantly passing through, exerting their own gravitational forces. These passing objects could occasionally disrupt the orbits of distant planets, including Pluto. Though such events would be rare and unpredictable, The combined effect of these varying forces may ensure that Pluto's orbit remains dynamic, constantly adjusting in response to the gravitational dance that occurs between the planets. On a more speculative note, the potential for a large-scale event, such as the collision of two smaller bodies in the distant reaches of the solar system, could also play a role in shifting the trajectories of objects like Pluto. If such an event were to occur, it might trigger a chain reaction that could impact Pluto's path in ways we cannot currently predict. This highlights the chaotic nature of celestial dynamics, where even minor events can lead to large-scale changes over time. Understanding these potential scenarios requires advanced simulations and continuous observation. While we currently have a good grasp of Pluto's orbital behavior, the true nature of its future trajectory will depend on a multitude of factors that are difficult to foresee. The ongoing study of Pluto, Neptune, and the outer solar system remains a crucial aspect of modern astrophysics, offering insights into the forces that govern our cosmic neighborhood.